Okay, in this section, we're going to talk about line spectra. Remember, we're talking about the justification or the discovery of quantum mechanics and the experiments at the turn of the century-ish, late 1800s, early 1900s, that were not understood and that were starting to be understood by scientists, starting with J.J. Thomson and the discovery of the electron. Well, the concept of line spectra came before J.J. Thomson and the discovery of the electron in 1897, but it wasn't understood. And so it was the experiments at the start of the 1900s that started to allow us to understand what was going on. But in 1885, Balmer looked at the spectrum that came from the hydrogen atom. And he found that the spectrum, and this was seen before in other things, that the spectrum that came from the atom was discretized, was discrete. There were discrete colors. It wasn't a continuum. It wasn't a rainbow. So let's just take a step back and just say, let's look at the sun. We know the sun is made of a number of things, but hydrogen's a big part of it. And what color is the sun? Well, the sun looks kind of orange, middle of the spectrum. But we know that if we take the sun and we break it into its constituent parts, that there are discrete colors that come from the sun. This is the concept of line spectra. Well, let's just go into that a little more deeply. The concept of line spectra is that it was observed that if you put energy into a gas, that kind of energy, right, heat or electricity or however else you can put energy in, there are other ways, it will emit a discrete spectrum of light. And this is the key here, is discrete spectrum of light. So let's just take, for example, not putting energy into a gas, but putting energy into a light bulb. So a light bulb is actually, we're not putting energy into a gas, we're putting energy into a dense wire and burning that wire, and you get out of the light bulb what we call white light. But if you look at that spectrum and you break up that light into its constituents, and we'll talk in a second about how you do that, you get sort of a continuum. You get the rainbow, right? You get all colors coming from a light bulb. Well, what you find if you put energy into a pure gas or a dilute gas, that doesn't happen, that you get discrete light. And we'll show this in class, but I'm going to talk about it here. So let's say, for example, we take a gas tube, a tube that we can put a dilute gas into, and we can put any gas into that we want, hydrogen, helium, lithium, whatever, and we put some energy into it. In class, we'll just put a voltage across it, and you're going to get light out. You can call that white light because it's a combination of colors. It may look blue, it may look red, it may look purple, depending on the gas. But what we want to do is break that into its constituent colors. So we break that into its constituent colors using what's called a diffraction grating. Now, you've heard of a diffraction grating before. A diffraction grating is just a bunch of slits, right? So we take that light and we run it through something with a bunch of really, really narrow slits. Lots and lots of slits right next to each other, right? And the example of diffraction or interference, this is an interference phenomenon that we've seen before, is taking two sources and having them interfere with each other, and you get light spots and dark spots. Well, here what you do is it's the same concept. It's just slightly more complicated. You take the light and you run it through a bunch of slits, creating what each slit does is it creates essentially an independent source. And those sources then interfere with each other, and you get an interference pattern. It's like the two-slit experiment. Hopefully you've seen or heard of the two-slit experiment before. But we take the two-slit experiment is just running some light through two slits, and it creates two sources, which then interfering, we can get an interference pattern. So we get an interference pattern, but what that interference pattern does is that the red, different colors of light will interfere constructively at different places, at different positions along a screen, because each of those colors has a different wavelength, so they interfere in a different place. So what a diffraction grating does, again, it's just a bunch of slits that take the light and break it into, as if it's now a number of sources that interfere. It'll break it into its color constituents, so we can then project that onto a screen, and the screen may be your eye, or it may be literally a screen, and so we'll get the red and the orange and the blue, or whatever's in the light will be split out, and whatever's not in the light will not be there. So what we see in line spectra is that only some of the colors appear. But not only that, not only do some of the colors appear, but that they're different for different gases. So not only is there a discrete spectrum, certain colors appear, not all colors appear, it's not a continuum, but no two pure elements emit the same spectrum. So this is now recognized as, while it's not understood why there's a discrete spectrum, it's recognized as a way to distinguish gases from each other, right? It's how we can figure out that the sun is made of hydrogen. We're looking at the spectrum of the sun. And we can tell what other stars are made of by looking at their spectra. So in 1885, as I mentioned, Balmer observed the hydrogen spectrum, and he observed that it was discrete, right? And that's what's important, is that there were only certain colors, and that they were very, very focused, right? That there was not a continuum at all. And so what and that is not understood. 1885, prior to the understanding of discrete quantities in physics, or prior to the understanding of quantum mechanics, one would think that everything, that the light that was emitted by something would just have some kind of continuous spectrum, maybe to do with its temperature or something, which is what we get to with blackbody radiation. In any case, Balmer in 1885 observed the hydrogen spectrum. He found empirically, you know what empirical means, right? Empirical means experimentally. It's not understood theoretically. It's not understood why. But he found empirically that he could describe that spectrum by this Rydberg equation, which is 1 over the wavelength equals a constant, r, which we call the Rydberg constant, times, and I know it looks a little weird, but 1 over 2 squared minus 1 over k squared, where k is an integer. It can be 1 over 4 minus 1 over k squared, where k is an integer, but you'll see why we said 1 over 2 squared later. And so it's the fact that k is an integer, that discretizes this equation, right? It's like this shows that there are independent individual colors. We'll see how that is in a second. The Rydberg constant, just by the way, Balmer determined, or Rydberg determined, I don't actually remember who Rydberg is 1.1 times 10 to the 7th inverse meters. And so anyway, so this describes part of the hydrogen spectrum. This actually describes the observable, the visible hydrogen spectrum. Well, later on, other scientists looked further at the hydrogen spectrum and found that there were other, what are called series. These are called series of spectral lines, so that this equation turns into 1 over n squared minus 1 over k squared, where k must always be bigger than n, otherwise it would be a negative number. And so this describes all of the lines, both the infrared and the ultraviolet lines that were seen from the hydrogen atom. And they're called the Lyman series for n equals 1, and the Paschen series for n equals 3, and the Brackett series for n equals 4, and the Funta series for n equals 5. But different scientists were able to observe different spectra at different wavelengths from the hydrogen atom, and were able to determine that this is a general equation. So the question here is, why is light quantized? Why does light come in discrete colors from these gases? There is just no understanding and no explanation. There's no theory that can say why light would be quantized. We have this empirical equation, and that's where we are right now. The question of why it's quantized comes much later on, when we start to understand quantum mechanics. So let's just do a trivial example, right? Let's plug in a number. Let's look at the Balmer series. Let's look for k equals 3. Plug that in. And, right, so the Rydberg constant, 1 over 2 squared minus 1 over k squared. And plug that in, and you get red light. So Balmer series predicts that hydrogen will emit red light. And let's look at k equals 4. Okay, that's blue-green light. So hydrogen will emit blue-green light. And we can do this for all the different combinations of integers, k and n, and remember that these are integer quantities, hence discrete light, hence quantization that's not understood. So in class, we'll just look at the hydrogen atom and look at the colors that come out, and we'll see red, blue, green, and whatever other colors come out. So that's pretty much all there is about line spectra. And again, we'll revisit line spectra when we come up with a justification, a theoretical justification of it. But the next thing is very, very closely connected, is blackbody radiation. Blackbody radiation is the spectrum that's emitted by a dense body. You might imagine that a table, a person, even the sun. I mean, it's more of a dense body than it is a dilute gas. Your computer, whatever. Your computer, I mean, any object emits radiation. You're just not really, you're aware of hot objects that emit radiation, like light bulbs and stove elements, right? Electric stove elements that glow red. But all bodies emit radiation of some sort. And you might guess that the radiation emitted by a dense body is much more complicated than radiation emitted by a pure dilute gas. And it is much more complicated. And what you see is you do see a continuous spectrum. Just because there's so many different atoms at different densities, and that's, now we're getting to the quantum mechanical reasons, but that you do see a continuous spectrum that comes from a dense body. But if we look at the electromagnetic spectrum, the light spectrum that comes from a dense body, and again, when I say light, I might mean ultraviolet light, UV light, infrared light, etc. So a table does indeed emit light. You just can't see it with your eyes because all you can see is a very, very small part of the electromagnetic spectrum with your eyes. So the first thing to note is that all bodies absorb and emit radiation. Oh, and let me just be clear that line spectra is about individual sort of colors coming out of a dilute gas, but in a dense body, there's a continuous spectrum. It looks more like you would expect classical physics, but we can't explain why the spectrum is the way it is, and that's what we're going to get to. So imagine looking at a plot of the colors that are coming out of a dilute hydrogen gas, right? And so we saw that red and blue were two colors that we expect. I put an orange in here too. I don't think that really belongs, but right. And so the intensity, I don't even know what the relative intensities are, but a graph would look sort of like this in the sense that the data points on the graph don't need to be colored, but I'm just showing that if wavelength increases, then red is the bigger wavelength and blue is the smaller wavelength. And a graph would just indicate data points, right? Independent, discrete data points. But for a black body will emit colors, which may not necessarily be in the visible spectrum, but let's just look at things, something like a light bulb or the sun or something, which may emit a continuum of colors. So a continuum of colors, sort of that might peak somewhere and go to might be some visible wavelengths, right? So we sort of these are the visible wavelengths. It might emit some lower wavelength, so that's ultraviolet light. It might emit some infrared light, etc. So a dense body might emit some kind of continuous spectrum that looks something like that. Let's just think about what we mean by a body emitting radiation. We're talking about electromagnetic radiation. We're talking about light. But when we say light, we mean it might be visible, RGB, red, orange, yellow, green, blue, indigo, violet, or it might be ultraviolet, it might be infrared, it might be anywhere, radio waves, etc., along the spectrum. Note also that a body which is in thermal equilibrium must absorb and emit radiation at the same rate. Oh, okay, what about this concept of absorbing radiation? Well, it's really important. We sort of ignored this. When we talked about line spectra, we talked about adding energy to a body to make it emit. But actually, bodies emit always. They must emit always. That's the part that we left out. It just may be that they emit light that we can't see, like a table emitting infrared radiation that we can't see. Low energy infrared radiation. And the reason why they must always emit radiation is because they're always absorbing radiation. So all bodies absorb and emit radiation. What do I mean by they must be absorbing radiation? Well, if there's a heater in the room, right, it's creating electromagnetic radiation, infrared radiation, and that radiation is bouncing off the walls and the tables and the people in the room. And it's not just bouncing, it's being absorbed by all of those things and it's heating them up. If there's a light bulb in the room, the light doesn't just bounce around forever, it's absorbed by everything in the room. So all bodies absorb and then hence must emit radiation. And the reason why they hence must emit radiation is because bodies don't just keep absorbing radiation forever. If a body only absorbed radiation and didn't emit radiation, it would heat up and heat up and heat up until it exploded, right? So a body which is in thermal equilibrium, if its temperature is not changing, then it must be absorbing and emitting radiation at the same rate. It's absorbing radiation from the lights and the heaters and the sun and anything around it. It must also be emitting the same amount of radiation it's absorbing if it's at a constant temperature. Most of the things around us are at a relative constant temperature, so that means most of the things around us are in thermal equilibrium, which absorb and emit radiation at the same rate. So a black body is just an ideal absorber. So we're going to start with an ideal situation of an ideal absorber, and then we can talk about any kind of body. So a black body, a table may be approximated as a black body. In other words, a black body does not necessarily appear black. The sun can be approximated as a black body. A person can be approximated as a black body. And so a black body is just an ideal absorber, and I'll explain what an ideal absorber means in a second. And then once we understand black bodies, we can then unidealize it and say, okay, we don't actually absorb all radiation incident on us. So let's just talk about what a black body is. So what an ideal absorber means that a black body is a body that absorbs all radiation incident upon it, all incident radiation. That means that all the sunlight, all the room light, all the heat coming out of the heaters is being absorbed by the ideal black body. What color does that mean it is? Aha, you might say, well, then it must be black because it's not reflecting any light. Isn't that the, what is it, the Fanta black or whatever that ideal black color is that they've now manufactured? Doesn't that make it entirely black? Well, here's the thing, is that if it's in thermal equilibrium, it must also be emitting radiation, and so it actually is not necessarily black. A black body doesn't have to be black because it may emit radiation in the visible spectrum. So I guess I never really thought about it, but that Fanta black, or I might be saying it wrong, whatever that ideal, black color is that scientists say they can produce now, it must be emitting, because if it's in thermal equilibrium, it must be emitting light too, but it must be emitting in a non-visible way, right? So an ideal black body absorbs all radiation incident, but it also emits radiation, so it may not be black, it may be a different color. If it's emitting it all in the infrared, because it's emitting it as heat, then indeed it appears black. But if it re-emits in the visible spectrum, hence a light bulb, that isn't reflecting light, it's emitting light, right? It's a difference. Reflection versus emission. Absorption and emission is it absorbs it, the atoms, we know now quantum mechanically, they get excited and then they re-emit light, as opposed to reflection where it bounces off, essentially. Okay, so anyway, so what color is it? A black body is not necessarily black, but what it means because it might emit in the visible spectrum, but what it means is it absorbs all radiation. Okay, I think I've said that enough times. So hopefully you understand what a black body is. You understand what black body radiation is. We haven't said anything about what's weird, right? What's weird? Remember, this was an experiment. This was something that was observed that wasn't understood. Well, remember this spectrum, right? We get an actually kind of expected spectrum. You get a continuous spectrum of light. All right, just make sure we understand. A black body may emit a continuous spectrum. It may emit across the visible spectrum. It may emit across an infrared, UV. The sun, if we idealize it as a black body, it's emitting UV, visible, and infrared. A table, if it's a black body, it's actually emitting way down in the infrared. Way down in the infrared. So, a table wouldn't have any of the visible light. But everything emits some kind of continuous spectrum. That's expected from classical mechanics, but it's the shape of the spectrum that's not understood. The shape of the spectrum cannot be explained by classical physics. It's this sort of bell curve-ish. It's not actually a bell curve because it's asymmetrical, but the bell curve-ish type shape cannot be understood by classical mechanics. So what is empirically observed is things that would be expected. So part of what's empirically observed is what would be expected. That the hotter the body, the more radiation it emits, okay? And that the hotter the body, I guess this maybe is not really understood necessarily, but that the hotter the body, the peak wavelength that's being emitted, so while there's a continuum of wavelengths, the peak wavelength actually moves to a lower and lower wavelength, or higher and higher frequency. So that's what's empirically observed. And so now we're trying to understand this, and I'll pick this up in class and try to describe what the shape of these curves is and what the problem is. But you need to understand the concept of the blackbody radiation spectrum, and that the shape, how it changes with temperature. That it's got a wavelength dependence, and the peak moves to lower wavelengths with higher temperature, and of course the body emits more radiation. This intensity of radiation that is emitted as the temperature increases.